Christoph Koutschan from Tulane and Tulane speak to us about both of Andrews and David Robbins q-TSPP Conjecture. As usual, we'll be taking Christoph out for dinner at the Evelyn restaurant at 6:45 tonight. If you'd like to join us, please let me know immediately after the talk.
So shall we start already? It's
Yes.
not yet 5.
Not? Oh.
So it's 2 minutes.
No.
I don't know whether more people are expected to come.
Doesn't matter.
I can start.
What time?
5.
Yeah, it's
Okay, so
it's fine.
my watch is wrong. Okay, thank you for the invitation. It's a great pleasure to me to talk here in the seminar and to present this result, which actually has been achieved in collaboration with my colleague Manuel Kauers from RISC Institute and Zeilberger, who's sitting here. Okay, let's start. The talk will be about a proof of some combinatorial results. So this was a famous conjecture about the enumeration of totally symmetric plane partitions. I assume that you don't know what this is, so I will explain it in a minute. This conjecture has first been posed by George Andrews and David Robbins, of whom I unfortunately could not find a picture in the internet, so I don't know how he looks like. Around 1983, so it's a quite old conjecture, more than 25 years old, and had not been solved until recently.
Right now he doesn't look very good because he's dead. But I used
Yeah, that's how I used to look. This conjecture became famous because it was part of this collection by Richard Stanley. He wrote this beautiful article, A Baker's Dozen of Conjectures Concerning Plane Partitions, and this q-TSPP conjecture popped up in this article, and it collected lots of open problems at these times. So this article is like from 1985, and one of these is the alternating sign matrix conjecture, and I guess you know who has proven this famous conjecture. It was proven by Zeilberger. And another version of, this is related to the q-TSPP. I will explain what the TSPP conjecture is. This had been proven in 95 and many others. So it's like a baker's dozen. Yeah, until now, so all of these problems had been solved, and except this q-TSPP stayed open for all this time. And you know that, there are some mathematical problems where you get a prize like $1 million if you prove P equals NP or not equal. I don't want to claim that this problem falls into this category, but there was also a prize announced for this problem, and it was $1,000. So it's like also something, and so this prize was offered by Zeilberger, and I'm very grateful that I now can receive this prize.
But to be honest, it's all offered to you if you do it.
So if anybody else, like if Krappenthaler had proven this conjecture, he would not have received the money. Okay, I see.
Or using this approach at least.
Yeah, okay. Now let's look at plane partitions. Just to recall, what is a plane partition? It's a two-dimensional array. And in each row and each column we have weakly increasing, decreasing numbers. So the best is if we look at an example. So this is an example for a plane partition. In each row the entries decrease, and also so in each column and in each row, as you can see. So, and this is expressed by these conditions. And for our purposes, it will be nicer to have a different representation of these plane partitions, namely what is called the 3D Ferrous diagram. And we get the 3D Ferrous diagram for a certain plane partition if we stack n unit cubes, where n is the number written in this field, onto this position. To make this clear, we look at this example, and we start in the left back corner and put 5 cubes there, because the entry 5 is there at this position. Then we put 4 cubes here, 1, 3, 2, 1, 1. So we obtain this 3D Ferrous diagram that corresponds to this plane partition. Okay, so this is a general plane partition. We are interested in special cases, namely plane partitions that are totally symmetric. And this means that all these cubes, the set of these cubes is invariant under the action of the symmetric group S3. So you can rotate, you can reflect. And again, I think the best is, so this is just another formulation. So whenever a position ijk is occupied, then all its permutation have to be occupied as well. Or the same for if it's empty, then all these other places have to be empty too. I will show a picture in a second and then it becomes quite clear what it is. And now if we look at such a set of cubes that we get by permuting the coordinates, then this set can have at most 6 elements, and these form a so-called orbit. We will also see this in the picture to make it more clear. And so this is the TSPP theorem or conjecture, and this was proven by John Stanbridge in 1995, as I mentioned. And if you want to count all totally symmetric plane partitions up to a certain size, so we bound it by the biggest entry in the plane partition to be n, then we get this nice product formula for the number of all such plane partitions. So here we have an example for a totally symmetric plane partition, and as you can see, you can reflect, you can rotate, and the structure will always look the same. Now, what about these orbits? There are basically 3 different cases. We can have orbits of length 1. This is, for example, this cube that sits on the position 4, 4, 4. And it's clear if we permute these coordinates, we always get 4, 4, 4. So this single cube forms a whole orbit. This is rather boring. You can look at other examples. Here we have an orbit of length 3. So this cube has coordinates like 7, 1, 1, I guess. And we have 1, 7, 1 and 7, 1, 1. So we get these 3 cubes that also form an orbit. And we can have orbits of length 6, as we can see here. So these cubes have the positions 2, 4, 6, I think. And of course we get 6 different permutations. Maybe this picture is a little bit misleading because it looks that all of these 6 come by rotation, which is not quite true. So we also have to consider reflection, for example, by this plane. So another example for an orbit of length 6 are the blue cubes. It's also an orbit of length 6. There is the reflection property. Okay, now how does this counting work?